ago by Hugh Constantine down in Australia. He was extremely young at the time. He's now doing his PhD, and he developed this to be open source, and it's been made open source from them. So what is that toolchain? It is essentially three major components and an optional component at the bottom. So let's go through the three major components. We have the compiler, which is developed for Windows, Linux, macOS, and other operating systems. You can compile it up. We give you the source code for 32-bit or 64-bit operating systems. You need a programmer to move the generated hex file into your selected microcontroller here, and you need a user interface. That user interface can be Edlin or Notepad. It doesn't matter. We don't care what it is, but I'll go take you through what we release for a number of the operating systems. So if we look at go back and focus on the compiler for a moment. So the compiler, as I said, is a source package, but we do distributions for Windows, Linux, macOS. I know there's a Pi release now, and we maintain a set of libraries that create the device libraries, and they are the things like displays, LCDs, and lots of sensors, etc. We maintain those, and we maintain a set of low-level libraries like Serial, I2C, SPI, EEPROM, etc. And they are ingested into the compiler, and I'll show you a diagram in a minute on how that works. So how do you know about your specific of your microcontroller? Well, we have a chip specification file called a DAT file, and we have a few thousand of those for all the different chip options out there, and we maintain those as part of the release. And that's where the LGT, we had to create new files there. We had to modify the low-level libraries to ensure that all these capabilities worked for this particular chipset. Alongside that, we have a couple of other things you should be aware of. We have help, and you've seen those during the tutorials. We have a list of reserved words, which may be useful to ensure you don't clash with the reserved words. You've seen a converter. You can write your own converters. The converter was used when we ingested a BMP and showed that on the graphics LCD device. And there are thousands of demonstrations, but the demonstrations are also the way we test the system. And you can leverage those as solutions or subcomponents of your solution, but they're very good baselines to get you up and running very, very quickly. That's how architecturally the compiler operates, but let's look at these other components. Well, you need to be able to program and via the programmer, and I've been using AVR-Do this week. There are lots of others installed in the distribution and available across a number of different operating systems are different options. Well, you need to be able to edit your source code through some user interface. You could use Notepad, but however, I've been using a thing called SynWrite, and SynWrite IDE has been developed so that it integrates with programmer preferences, which is the way that we control the communications ports, and it integrates with the helpers. That's when you type, you get strings come up, and it integrates so that you've got hotkeys, etc. And those aren't the only options that we provide. We've also got a secondary option that is called a Great Cow Graphical Basic, which is here. And the Great Cow Graphical Basic was also developed by Hugh. And you should look at that. It's a very good tool. Now, clearly, the programmer preferences I mentioned integrate with programmers. So there's an integration line there, and that, if you're using the Windows solution, that's all supplied as an integrated solution. Worthy of note are things like terminal software on your PC. We provide terminal and PuTTY in the Windows distribution. You'll need to find something else for other operating systems, but they're very good for debugging and that user interface experience for your users. Solution. So let's have a look at how it works in terms of the core compiler and how we take your source code to generate a hex file. We take your source code and we start to pre-process that here where we check for syntax, and we bring in and merge in the libraries. Well, as it progresses through the preprocessor, we now know what you're up to in terms of your program. You know, are you using EEPROM, are you using I2C or not, just inputs and outputs, and it does that validation for you. And you might get error messages and syntax errors from the preprocessor. We translate this into a code translator, and that code translator starts to shape your program for your target architecture, be that a PIC, and there's has to be 20 different types of PIC families that are available. You've got all the AVR range, I think there's 5 in there, and now the LGT range. And it takes that and puts it in a format that is preparing it for the next major step, which is the assembler. It creates raw assembler that you can then examine to learn assembly. You can also see how we took your source code to generate an ASM file. At the same time, we generate reports that you can look at to examine and optimize your own code. But you'll see here that the assembler is an output, and that is called an ASM file, and you can see that next to your source file. Well, if your command switch is just use Great Cow Basic, it will then link it. It will then link that out and generate you a hex file. This only takes a few seconds. You've seen that quite large programs only take a few seconds because the core compiler is a single executable. Just clear those down. Let's look at some other options that you've got. Well, if you want to change the way that you program, you want to use your own linker, you can just change the command line switches that calls the compiler. And what it will do, it will take your source code, as it did before, it will merge it with the libraries. It will then take those two through the code translator into the assembler. It will generate the assembler file, and it may stop there. You may decide for it to go direct into another linker or another tool like WinAVR, Atmel AVR, Studio, etc., and use those. Use those to generate your hex file. You can then take those hex files and then use your own programming control to program it, which is the red line up here. So we give you lots of different options, but Great Cow Basic is essentially a soup to nuts solution, or as shown in this diagram, you can actually take the assembler and examine it, change it, modify it, and then program it through your own programmer control. That is fully supported. I have shown you the previous diagram, a soup to nuts solution. Tomorrow, in the next tutorial, we'll look at some of these other options. Just clear down those marks. So that's where I wanted to sort of leave the tool chain. Remember the previous 2 slides back, the compiler itself is made up of these components, the compiler, the programmer, the UI, and optional tools like the terminal. So the tool chain is extremely simple. It's extremely simple to install, and it's extremely simple to use. So today, let's have a look out on the lab to see what we've got. Some excitement here out in the lab. Well, we've got some excitement. Look, I've taken our little board here, and I've made some. I've made a little voltmeter. It's quite clever. Look, quite clever. It's not really. Look, I've made a voltmeter. I've taken the ADC, and I've made a voltmeter. Let me zoom in on that for you so you can see it. I rotate the pot. 0 is full off. There we go, look, that's hovering there. Now, what I've also done is I've taken all the programs. So I've just shown you a quick voltmeter. That's just to show you that you can really develop solutions in this. I've taken all those programs in all the tutorials and I sort of put them into one program. So I've got LEDs, pulse width modulation. I've actually written a sprite routine, external interrupts, sound. I've done quite a lot of changes, but I've just taken what we had before and compiled it up. So let me just nip into the compiler here. It is exactly the same program as before. I've got chip set up the same. I've got serial set up, GLCD set up, all the ports. I'm just going to compile that up and then we'll see what it does out in the lab. For those who've got really good sound, you might have heard some clicking in the background. That's a sound, because you can do sound. As you can see, I've got a very small little sprite here bouncing away, and I've got LEDs rotating. I've got pulse width modulation on the yellow LEDs at the bottom. I've got an external interrupt here to reset my chip. I've got sound, all in one program. The program itself has used 1148 bytes of RAM, because this is using a memory cache for the GLCD, and the program itself is actually only using 25% of the resources, so it's a very small program for this chip. So what I want to show you today is some very simple demonstrations. I also wanted to show you the tool chain itself. So with that, I'll call that a wrap. Enjoy.